Okay, so we left off last time talking about random number generators and different algorithms for generating these pseudo-random numbers. And we saw an example of a fairly simple one called Witchman-Hill. And the idea is I want to finish off talking about random number generators. I'll just talk a little bit about this one that's used in R called the Mersenne twister. That's the default in R. And then we'll talk some about generating random numbers that'll work if you're doing things in parallel. And then we'll switch gears a little bit and talk about some algorithms for generating random numbers from a particular distribution when you have trouble, when it's hard to generate from that distribution in any analytic sort of fashion. Okay, so the idea of the Mersenne twister, we're not going to go into a huge amount of detail, is basically as follows, that there's this sort of class of generators called generalized feedback shift registers. And the idea is you have some method for generating a pseudo-random sequence of bits, so zeros and ones. So I'm thinking of sort of generating this way. And I'm trying to come up with a recipe that will generate random zeros and ones. And then I'm going to use that sequence of zeros and ones to generate random uniforms. So the basic idea of the Mersenne twister is that you come up with basically that based on two of the previous bits in the sequence, you combine those with the exclusive OR operator. So 0 plus 0 is 0, 1 plus 1 is 0, and then 0 plus 1 or 1 plus 0 is 1. So we're going to combine these two bits and get this bit. And the idea is the developers of the algorithm, presumably somebody named Mersenne, carefully chose which of these two to combine to get this one. And then this next one is going to be based on two previous ones in the series as well. So that's going to generate our deterministic sequence of zeros and ones, but in such a fashion that these behave as if they're a random sequence of bits. And then the idea is we take L of them, so we're going to have, the result is we're going to be able to represent to the L distinct different numbers. We take L of these bits, so from here to here, and we take that, go from base 2 to the base 10 number that represents. And then that's going to give us UK, and the next block will give us UK plus 1, and so on and so forth. And then to make sure that this is between 0 and, that the numbers here are between 0 and 1, so that they're actually random uniforms between 0 and 1, we just need to divide by the largest value that we could get from taking a sequence of L different bits and converting that to a base 10 number. So that's the basic idea of the Mersenne twister, and that is actually the default in R, and I forget off the top of my head, it's either the default in, I think it's in the default in Python as well. And if you look at, we talked a little bit last time about the seed in R, and so we saw with Witchman-Hill that you can give R, the set.seed function in R, you can give it a single number, and what it's going to do is then somehow generate those three values, which are the seeds for Witchman-Hill, which we saw last time. It turns out that if you look into the details in R, that the actual seed when you're using the Mersenne twister is actually a sequence of 624 different numbers. So somehow there's some recipe, I don't know the details of it, whereby R, when you give it a seed that's a single value, when it's using the Mersenne twister, when that's set as the default, as the random number generator, it'll then take it'll take that single number that you gave it, convert it into these 624 numbers, and that's actually what's determining the seed here. And I presume, although I haven't looked into it, that the 624 numbers are basically the sort of 624 numbers of these kinds of numbers, and that basically tells you where you are. And yeah, so and then since that gives us a whole long string of bits, we can then bootstrap our way forward to continue simulating from wherever we are in this sequence. Okay, so questions or comments at this point? Okay, so I said last time that it's a really good idea to set the seed before you do any random number generation so that you can go back and exactly recreate whatever calculation that you were doing. So let's just see a quick example of that. There's something, I haven't delved into this enough to sort of figure out what's going on. The Gentle book says that in R, the input to set that seed should be an integer between 0 and 1023. And that each of those 1,024 values is going to give you a place in this very long, is going to be, so in some sense, far away starting point in this very long sequence of pseudo-random numbers. Turns out you can pass in numbers like -2 or 2033, which is bigger than 1023, and it still seems to behave fine. So I'm not exactly sure why Gentle has that reference in there. But let's just see a quick example of this. This is not going to be complicated, but here we're just going to see, okay, if we set the seed and then we generate 10 random normals in this case. It turns out that to generate a random normal, you just basically take 2 random uniforms, and there's an algorithm that will then generate a normal from the 2 random uniforms. If we then reset the seed and... oh, thanks. Okay, I was like, that should have worked. Okay, so let's try that again. Okay, so, oops. So here I've set the seed twice at 0, generated 10 random normals. You can see I'm getting the exact same random normals, so that I'm able to do this in a repeatable fashion. And I can do things, I can play games like this. I can set the seed, generate 5 random numbers. So these are the first 5 of the 10 that I've already generated, of course, because I set the seed to 0. I can save the seed, and the seed is stored in .random.seed. So I'm going to save that into an object called saved seed. I'm going to go ahead and do something that involves random number generation. I don't really care what. This is just to make the point that I can go off and do a whole bunch of other random number of calculations that involve random number generation, in this case using the sample function. Now I'm going to take the saved seed and put it back into .randomSeed. So that's what I'm doing. That's what I'm about to do here. And now if I generate another 5 random normals, what we should see is that I basically got back to where I was, that I generated the first 5 of the 10 that start when I set seed to 0. I went off and did a whole bunch of other stuff, but I saved the seed and put put the seed back into .randomSeed, and now the next 5 that I generate correspond to the 5 that I would have generated if I just generated the 10 initially, instead of generating 5, doing a bunch of other stuff, and then coming along and generating the next 5. But that just shows that we have essentially complete control over where we are in the sequence, and we can play games like this if we need to get the behavior that we want. Okay, any questions about that? Another thing, let's see. Yeah, you could do this in, if you wanted to do this in a function, you could do something like this. You could save the seed into what here I'm calling old seed, and then globally assign back into .randomSeed with the double arrow assignment operator. Okay, so I think that's all I want to say there. Oh, the other thing I'll mention is that I have this point made here that based on how R is doing the calculations behind the scenes, for example, with the Mersenne twister where we've got these 32 bits that are representing each random number, we only have 2 to the 32 distinct different values that we're going to be generating from when we're generating our random uniforms. That doesn't mean the periodicity is only 2 to the 32 because the calculations behind the scenes, because the periodicity of a generator like this is, it's not, what am I trying to say here? Because of the way that the bits are being generated from back in the stream, you can work out that, for example, the periodicity of the Mersenne twister is just incredibly long. It's like 2 to the 19,937, so it's just a really long periodicity. But within that within the periodicity, so this is the idea of I have the circle, and to get all the way around the circle takes 2 to the 19,937. But because of the fact that I'm only representing the results of generating these random numbers as these 32-bit integers, there are going to be repeats of values in the sequence. So this value and this value might be the same, but this value and this value are not going to be, these two values are not going to be the same. So it's not like the periodicity is shorter than guaranteed. It's just that we will get repeated. We're not going to have, these are not 2 to the 1937 unique values in here. It's just that the periodicity of the point at which we start repeating the sequence again is quite long. Okay, so let's talk about a little bit about generating random numbers in parallel, which sort of goes back to this thing that I've drawn here. So basic story here is one of the main. There's sort of a really bad way to do this. There's an okay way to do this, and then there's a really good way to do this if you want to generate random numbers in parallel and have your work being done in different chunks. So basically, what we'd like to do is if we've divided up our work into, say, p different tasks, we'd like each of those p different tasks to be using a separate subset of these random numbers in this periodic sequence. So ideally what we would do is, suppose we have 10 tasks. Well, ideally what we would like to do is make sure that that our 10 tasks are using different blocks of the sequence. So maybe we're doing 1, 2, 3, 4, 5, 6. I'm sort of filling in them in somewhat far apart from each other, such that the numbers that I use in the first task don't overlap with the numbers that I use in the second task or that I use in the third task. Okay? So we might be safe if we just set the seed for each of these tasks to be a different number, and then rely on this idea that somehow or another that the way the seed is set up is that these things are sufficiently far apart from each other that we're going to be safe. There's no guarantee that that's actually going to happen, and the possibility is that we might sort of get unlucky and have the first seed the seed that we set for the first task be there, or maybe the seed we set for the second task is there, and then maybe I'm generating this many numbers for the first task and this many numbers for the second task, and some of them overlap. Okay? Depending on how you're using the random numbers, that could be a problem. We now have basically a dependence between the numbers that are used in the first task and the numbers that are used in the second task, and that could then cause problems in whatever you're doing with them subsequently. So the idea is we'd like to avoid that. It's somewhat unlikely if you just set the seed to be different values that we're going to have this kind of overlap, unless you're generating really, really long subsequences of random numbers in each of the given tasks. But the idea is that a more sophisticated approach would actually ensure that we're generating from distinct subsequences here. So one idea is, well, if I have a random number generator where I can control this, suppose I know how many I'm going to generate in each of my tasks. What I might do is say, okay, I'm going to generate, suppose this is how many I need to generate my first task. Well, I'll set the seed so that I'm here and I generate them. And then for my second task, I'll set the seed to pick up basically where the first task left off and use these for the second one, and use these for the third one, and use these for the fourth one, and so on and so forth. So that would be the idea of ensuring that these are distinct subsequences that are passed off to each of my parallel tasks. Okay, so questions about the big picture here? Yeah.
So are all the seeds like evenly separated?
Yeah, I'm not actually sure, and when I haven't delved into this a great deal, but the only thing I've really seen is just this idea that in general they're fairly far away from each other, but I don't quite know what that means, and I don't know what the algorithm is that determined that. So that sort of gets to this idea of why we want to do it in a safer fashion, because we're not sort of exactly sure what's happening when the seed is being set. Well, so one idea is, and this is sort of a naive idea, but it would work, is I could just generate all of my random numbers on the master process, and then if I know that I'm going to need 10,000 random numbers on each of the workers, well, I'll just manually divide them up myself. I'll generate them all, I'll take the chunks and I'll pass the chunks off to the workers, and I'll let the workers use those random numbers. So you can probably sort of see what the downside is. Well, I have to communicate all those numbers to the workers, and if a large part of the computation that I'm doing is actually taken up in generating the random numbers, well, I'm not doing that in parallel, so it might be slow if I do that all in the master. So I might sort of shoot myself in the foot by taking that approach. Okay, so that was what I termed the clunky but effective approach, is to do it all in one place. The more sophisticated approach is to use one of the random number generating algorithms that actually ensures that these things are distinct subsequences or subsets of the sequence. So there are two packages in R that do this. There's one called R-Lecuyer or Lecuyer. So I guess this guy's French, so it's probably Lecuyer. And that's in the R-Lecuyer package. There's also R-Spring, and that's another package that does something like this. So we'll talk a little bit about this Lecuyer algorithm. So basically, it's a different random number generator. It's not the Mersenne twister. But it has a periodicity of 2 to the 191. So that's how long it takes you to go all the way around the circle. And it divides that, the circle into 2 to the 127 different subsequences, distinct subsequences. And then the idea is the code is set up in such a way that it ensures that each of the, depending on how you set up, each of the workers or each of the tasks is getting a distinct subsequence of random uniforms from this pseudo-random sequence. So that's the, so basically the idea is to exploit this sort of algorithm. And I'll show a little bit of the syntax of how you do that in R. I actually have sort of a lot of the gory detail in the notes in case you need to come back to this and do this for different kinds of parallelizations that you might be doing. But there's not a lot of point in going through all of those. So here's one use case of how you might be using this. So we load the parallel package, we load this R-Lecuyer package, and then I'm just going to have some test function that I'm going to run repeatedly on different workers. And so this is just going to generate, in this case, just one random number, just so there's some random number generation in the code that's being done as in parallel on the workers. Okay. Okay, so now what I'm going to do is I'm going to see what's the current default random number generator is the Mersenne twister. I'm going to make a cluster so that I can then use par-s-apply. This goes back to what we saw in the parallel unit. I'm going to set this thing that I'm calling the seed, which I'm calling iSeed, to be 0. And then I'm going to do cluster set RNG stream, and this is part of the Lecuyer package. And basically this says, okay, with this cluster that I'm creating of the 4 different workers that are going to do the various tasks in parallel, set the seed to be, in this case, 0, and then this is going to go ahead and use the Lecuyer algorithm. It turns out if you actually look and see, it doesn't look like it's changed anything in the master process, but it is actually using the Lecuyer algorithm on the workers, so it is actually working. And then what I would do is I would then just go ahead and do whatever par-s-apply calculations I want to do. In this case, that's just going to generate some individual random uniforms. I guess I set n sims to be 250. So I've got 250 tasks. I've got 4 workers. I'm dispatching the 250 tasks to the 4 workers, and each worker is doing some subset of the tasks. If I want to reset the seed to be back to what it was and show that I can get repeatable results from doing this, I can just do this again. I can do set RNG stream with that same iSeed being 0. I can repeat the calculations, and I should see that res and res2 as a result are identical. And then this will just stop the cluster. So it's fairly straightforward as long as you sort of have a template of how to go about doing it. Any questions about that? Yeah.
The ordering of the process depends on how is queued in a sequence. For instance, you have 250 numbers to generate, then you split that into 4 cores, right? And whether you take, say, the first 2, the first 60, or whether it's jumping around.
Right. Yeah, so that's a really good question, and I'm glad you brought it up because I think I might have forgotten to mention it, which is that there are basically you basically have to have an understanding of how the tasks are being dispatched to the workers. So in this example, I had 4 workers, but I had 250 tasks. And the question is, how are these split up amongst the workers? And is this random number generator giving a unique seed to each of the workers? In which case, suppose that suppose worker number 1 gets tasks 1, 5, 9, 13, and worker number 2 gets tasks 2, 6, 10, 14, etc., etc. Well, if the random number sequences are unique to the workers, then task 1 will use the first set of random numbers that are generated. Task 5 will use the next set. Task 9 will use the next set. Similarly, with worker number 2, it'll get a set of random numbers. Task 2 will use those. Then the next set in the sequence. Sorry, I think I was saying that in probably an unclear way. If the subsequences are unique to the workers, there are only going to be 4 subsequences. So this is going to be the subsequence for worker 1. Task 1 is going to get however many it needs. Task 5 is going to get however many it needs, and so on and so forth. It's also possible that maybe the random number sequences are unique to the tasks, in which case there are going to be 250 of these, and each of the tasks is going to get one of these subsequences. So basically, you would need to sort of, if you were, and then the other aspect of this is repeatability, which is if the random number subsets are unique to are divisioned up by worker. Well, suppose that I then try and repeat this calculation, and the next time I do the calculation, worker 1 happens to get 1, 5, but then it happens to get 10 instead of 9, and then 13. Well, in that case, if I do that identical, the result of this is not going to be identical to the result of this, even though I've still ensured that each of the workers is getting a distinct subsequence, because of just the random variation that in this case, the way the tasks were divided amongst the workers was different. So basically, in order to, if you're worried about this, you sort of just need to delve into the details and see, are the tasks being split up in a way that's repeatable across when I repeat the operations, and are the subsets of the random number sequence unique to the workers or unique to the tasks? So I don't think we need to go into the details, but that is, if you were doing this, then that might be something that you need to think about. And I think I have a few more comments about that in the notes as well. If you want to do this, if you're using, for example, MCLapply, you can do it in this fashion. You can set the RNG kind to be this LeCuyer algorithm. And then all you need to do with MCLapply is just provide one additional argument, which is this mc.set.c, and just say that's equal to true. And then if we run this again and set the c equals true, this will then be repeatable, and the results will be identical between the 2 different times that we ran it. And then I also provide some template code of how you would make sure that if you're using for each, you're going to get distinct subsets of random numbers when you're using for each. And there's also, sort of going back to Darren's question, there's also this issue that might arise with for each. So there are some mechanisms in place where you can make sure that things are repeatable when you use for each. So it's sort of a lot of details and nothing particularly interesting intellectually. It's just sort of making sure that you keep track of things. So I think I'll leave that at that. But there is a lot of detail in the notes on that. Okay, so any questions before we jump ahead to methods for generating random numbers from particular distributions? Yeah.
So are we just treating this as a LeCuyer algorithm as like a black box where like we're just saying it's completely faultless, so let's just use this for everything?
Yeah, I mean, it's a pretty well-established algorithm. If you wanted to, it wouldn't be hard to look up the underlying journal article that talks about it. I don't actually know off the top of my head what the details are of how it works and how it divides up. This is no longer that big. This is the 2 to 191. How it does the division into the 2 to the 137 distinct sequences. But it's pretty well established, so I think we can trust that it's doing things correctly. Yeah. Other questions? Okay. One of the nice things about a language like R is because it was developed by statisticians, we think a lot about random number generators. We worry a lot about random number generators. And so unlike a package, unlike something like, say, Excel or some other software that wasn't developed by people who are in the business of dealing with random numbers, you sort of have some reasonable assurance that whoever wrote the stuff for R was thinking about it carefully because of the fact that this is sort of our bread and butter in terms of the sorts of things that we need to do. Which is not, of course, to say that there might not be errors, or that if somebody writes some add-on package that does some random number generation, that there might not be errors in that. Okay, so let's move on and talk about generating numbers from particular distributions. I have a little bit here if you want to, just to remind you of how to generate from a random normal. There's also a package called MVT norm that deals with random multivariate normals and multivariate t's. Everybody should, I think, have seen the inverse CDF method for generating from a distribution when you can actually invert the cumulative distribution function. If you don't know how to do that, you should go look that up, but I'm not going to take the time to do that here. So now what I would like to do with the remainder of the unit is just talk about a few different sampling methods that are basically available to us if we can't easily generate from some density of interest. So the idea is we have some density f, and we can write down and evaluate that density f for any given input x. So we could, for example, make a plot of this density by just evaluating f at some grid of points. Or this might be a multivariate density. But we don't have a recipe by which we can generate random numbers from this distribution. Okay? Unlike the random normal or the random gamma, or unlike the normal or the gamma or the t or something like that, we don't have a standard recipe by which we can generate from this distribution. So there are a few different strategies that we can take when we come across this situation. Okay, so the first of these that we're going to talk about is something called rejection sampling. And so the idea is to first look at this problem in a slightly different way, which is to say, one way that I could think of generating from this distribution is basically to introduce an auxiliary variable. And the idea is that auxiliary variable is going to be the height along this axis here. So I'm going to call this u. And what I'm going to say is, okay, I'm going to have a two-dimensional bivariate distribution on x and u, although I think I want to call this y for the moment for reasons that will become apparent. So the basic idea is I'm going to define a uniform distribution that is uniform within this area here. Okay, so this is basically going to be I'm going to have a uniform distribution on this shape here, such that it comes out of the board and is flat, however far it has to come out such that it integrates to 1. So that's a uniform distribution over this somewhat funny shape. And then the idea is if I think about the marginal distribution for x, the idea is that what I can do is I can basically, how do I want to say this? Well, okay, let me say it this way. So the basic idea is if I want to know what the probability of x less than or equal to x is, what the marginal distribution is, if I draw u and x jointly from this distribution, then what is that? Well, that is going to be the integral from minus infinity up to x. Of, if I want to know what's the probability that x, that the variable is less than here, well, the way that I would find that out is I would integrate over this shape here up to this point x. So I'm going to integrate from minus infinity to x, and then I'm going to integrate from 0 up to u. Well, u is just going to be f of x. This is a uniform distribution on the shape, so that's going to be a 1. And then I'm going to do what am I doing here? du dy. Oh, sorry, this is a y. Okay, so I have a dummy variable y that for any given y, I'm just integrating from 0 up to f of y. So if I go ahead and do this integral, then this is just going to be the integral from minus infinity to x of f of y dy. Well, that is just the CDF of x. The CDF for this random variable x. Okay, so that says, okay, that the marginal distribution for x, if I have this bivariate distribution, is just the distribution that I want, which is the original density f with its CDF capital F. Okay, so the question is, how does this help me? So I've sort of set this up, but we haven't really said where I'm going with this. So the idea is that suppose I can basically find some other density that if I multiply it by a constant is always above the density f that I'm interested in. So I don't have an easy recipe for generating from below this curve, but I'm able to find some envelope like this such that I can actually generate from this envelope here. Well, then the idea is that if I can generate from this envelope here, the way that I make sure that I'm actually generating from this bivariate distribution here that's uniform within this shape here is, okay, I generate from this distribution here, and then I draw a uniform distribution between wherever so suppose that I generated this value here. Okay? Then what I'm going to do is I'm going to draw from a uniform distribution, and if I am basically, if the uniform value that I draw is basically below here as opposed to above here, then I'm going to accept the value that I draw, and if it's above, I'm going to reject it. So the result is I'm only going to draw values within this shape here, and I'm going to reject anything that gets drawn above the curve here. So that's the basic strategy. So just to sort of reiterate what I have here written down is generate from this distribution G. So the idea is that we're going to make sure that if I take some constant and multiply by G, that's going to be bigger than the f of interest. Okay. So this is going to be C times G, and this is going to be f of x. So I'm going to generate x from G, and G has to be something that's easier to generate random numbers from. And then I'm going to generate this U that's uniform 0, 1. And then if the U is such that it is less than f over C times G, that's basically just saying if I'm generating a number between here and here, if it falls here rather than it falls here, then I'm going to accept the point. And if it falls here, I'm going to reject it. And so I'm just going to keep doing this procedure until I collect enough values that I've got a large enough sample from my distribution f. So that's the basic idea. As you would expect, that what we'd like to have is an envelope that doesn't rise too far above f itself, because all of these points here are going to be wasted computation, and we're not going to be able to use them. And so it turns out that the acceptance probability is 1 over c, based on doing this little calculation here. And so we'd like for c to be small. We'd like to not have to multiply g by a very large number in order to have c times g be above f everywhere, above or equal to f everywhere. Let's see. Okay, so I've sort of drawn this in an example where I just have a bounded interval here, but we can do this over the entire real line. So let me pose a question to you about doing that. So suppose, just for the sake of thinking about an example, suppose that I wanted to generate from a normal distribution. Can I use a t-distribution as the distribution that I actually sample from? So pretend I don't have an algorithm for generating from a normal distribution. Would I be able to use a t-distribution as my g of x? So this would be f, and this would be g. And conversely, suppose I wanted to generate from a t-distribution. Can I use a normal distribution as my g? So what do folks think about those two questions? You're nodding your head. Does that mean yes for both? Yes for one? Yes for both? Okay, so what do I need to be able to do? I need to make sure that I can find some c that if I multiply it by g, it's going to be bigger than f everywhere. Because that's, if this goes below, then I'm going to have problems because I need to be generating in this particular way. So what happens here, if I have a normal distribution, so here's the normal, and now what does a t look like? Well, a t has fatter tails, right? Actually, I don't, does anybody remember whether a t is higher than a normal here or not? I'm sort of forgetting what the shoulders look like. Anybody know? Huh? You think it's higher? Okay. So it looks sort of like this. Okay. Well, what needs to happen? I need to multiply by some c so that wherever the t is below the normal distribution, it lifts it above it. Right? So, okay, suppose, so that means I need to multiply by c that's big enough so that this whole curve gets lifted above, so it's above it everywhere. Well, is that going to work out in the tail? So the tail of a t distribution is already fatter than a normal distribution, right? So once we get far enough out in the tail, the t is already going to be higher than the normal distribution. We don't actually have to multiply it by anything to get it above the normal density. So whatever c works here in the body of the distribution to get the t above the normal will work out in the tails as well. And so this recipe should work in that case. But now let's think about the converse situation and about the tails. What if I'm trying to raise the normal above the t distribution? Well, the normal tails decay exponentially fast. The t-tails decay polynomially fast, and so the t-tails are decaying much more slowly than the tails of the normal distribution. So I might here, I can determine a c here in the middle of the distribution that will raise the normal above the t distribution to try and find my c. But basically, everywhere out here in the tail, I'm just going to have to keep raising the normal distribution more and more and more as I get further out in the tail because of the fact that the normal distribution is decaying at a faster rate than the t distribution is. So, I'm sort of exaggerating here, but basically the normal distribution is doing this. The t distribution is doing this. They're getting farther and farther apart in relative terms. And so as I go further out in the tail, I just have to make that c bigger and bigger and bigger, and I can't find a constant c that will get the normal tails to be above the t-tails. So you have to think carefully if you're going to play this kind of game, you have to think carefully about whether I can find this c that will hold throughout the distribution. And the real thing you end up having to worry about is how do the two different tails behave. Okay, the other thing I'll mention is that there's another idea called squeezing that comes into play sometimes when people are doing this sort of exercise. And it's sort of a computational trick, which is, let me just redraw this actually. Suppose I have some distribution. I have some upper bound c times g of x. Suppose that this actually evaluating f of x is computationally expensive. So the idea is maybe this f of x is just some really hard thing to evaluate, and it just takes a lot of computation to actually find f as a function of x for some x, for any given x. Another thing that you can do sometimes is have, maybe it would be hard to come up with one when I draw it like this, but suppose f looks like this. Sometimes you can come up with a lower bound that always falls below the f that you're interested in. And in that case, when I'm going through my recipe, and I draw my u, and I want to see whether I'm here or here to determine whether I accept or whether I'm here or here to determine whether I accept or reject. If I have a lower bound and I see that the value falls, that the u falls below the lower bound here, then I never need to evaluate f of x. I can just evaluate the lower bound. If I find out that it's above, then I still need to go ahead and evaluate f of x to see, well, am I in this portion or am I in this portion? But if the lower bound is sufficiently close to the function of interest, then for many of the values that I draw, I may be in this portion of the domain and I don't actually need to evaluate the function f. So that's called squeezing. And the idea is to have this lower bound that saves us some computation. Okay, so questions or comments at this point?
So I assume for the lower bound you're like using polynomials or something to approximate it?
It sort of all depends on exactly what density you have as to whether you can come up with a clever choice of what the lower bound is. And I imagine that there may be sort of some standard tricks for doing this. I don't happen to know what they are, but I don't know that there's any particular. What we're going to see in a minute is a recipe for doing this in a sort of automated fashion. For sort of the arbitrary case of doing rejection sampling, I don't know that there's any automated way to do this. Okay, so the next thing is this idea of adaptive rejection sampling. So part of the difficulty with rejection sampling is, well, how do I come up with this G? I need to make sure that I can find the C. You know, you end up having to do some analysis to sort of figure out. You have to sort of come up with a candidate. You have to do some calculations to figure out the C, and it may be a hard thing to do. And we have to sort of tailor make it for every individual case that we come across. So the idea of adaptive rejection sampling is to actually have an algorithm that will work in general. So adaptive rejection sampling, it gives us an algorithm. It only, however, works under particular conditions. So it has to be a continuous differentiable log concave density. So basically what that means is when you take the density f of x and you take the log, the result is a concave function. So we have to have that log f of x is a concave function. The normal, for example, works because the normal distribution is exp of minus 1/2 x minus mu squared over sigma squared. If you take the log of that, that's just a quadratic function. It's just x to the, it's quadratic in x. So when I take the log of a normal distribution, what it looks like is it looks like this. That is indeed a convex function. I can take any 2 points and draw a line between them, and the line is going to be below the function throughout. Okay. It doesn't, for example, work for a t-distribution, which is not log concave. Okay, so the idea is, suppose we do have one of these log concave densities. They arise fairly frequently. The question is, how do we come up with, so this is now log f of x. The question is, how do we come up with an upper bound, and also actually how do we come up with a lower bound that allows us to do sampling in an automated fashion? Well, so you guys should be paying attention because this is writing up the code for this problem is the project, the final project for everybody. So the idea is we're gonna start with a set of points, x and their corresponding f of x values. And you can do this either by drawing secants that connect the points, or by drawing tangent lines that go through the points and are parallel to the curve at the point. I guess we'll just try the tangent version here. So what am I going to do? I'm going to draw a tangent here. By virtue of the fact that this is a concave function, I know that this is going to be above the function everywhere except where it touches. Okay. Now I'm going to draw another one here. I'm going to draw another one here, and I'm going to draw another one here. What have we done? Too bad I don't have another color. If I think about what I've done, I've basically created an upper bound. So here's the upper bound to this point. Then at this junction point here, I switch to this line. And then here I switch to this line. And here I switch to this line here. So I've traced out an upper bound for my function there. These are straight lines in the log space. So if I exponentiate back, I'm basically going to be working with piecewise exponentials between the junction points here. So if I were to try and sample from here to here, I could sample from an exponential distribution that was suitably shifted. And I'm going to have a number of these piecewise exponentials. So those are easy to sample from. So I can easily sample from my upper bounds. So that sort of alleviates the difficulty that arose in rejection sampling of how do I come up with this G such that G is easy to sample from? Well, I have a recipe for doing it here. And the other portion of this is to actually have a lower bound. And so the lower bound can be obtained by just going straight up to the point here, then drawing a straight line to the next point, straight line to the next point, straight line to the next point, and straight down. And you can see it's sort of getting a little lost in all of my chalk here, but again, by virtue of the fact that I've got a convex function, these are going to always be below the actual function f. So if we can try and sort of abstract this away from what I drew here, I have this lower bound that looks something like this. Oops, sorry. And I have this upper bound that looks something like this. And what is the recipe? Well, the recipe is I'm going to sample from the upper bound. So I'm going to call that, what notation am I using here? I'm going to call this upper bound f sub upper n of x. The n is because for the moment I'm using a certain number of points, but as the recipe proceeds along, I'm going to add points along the axis and refine my upper and lower bounds. So I'm going to draw from this distribution. Okay, this is not going to be a distribution unless I normalize it, but it's easy to draw from this upper bound. It's an unnormalized density. And it's an unnormalized piecewise exponential density. So I'm going to draw from that, and then I'm going to draw a u that's uniform 0, 1. So has the same flavor as the rejection sampling that we just saw. So if u is less than or equal to f, and then the lower bound I'm going to call f underscore n of x. So if u is less than f underscore n of x over f upper bar n of x, then I'm going to accept the point and add it to my collection of random samples. And if it's not less than the lower bound, I have to do a little bit more work, and I actually have to evaluate f to see, am I below f but above the lower bound, or am I above f and below, and of course I'll have to be below the upper bound. So then if I don't accept otherwise, I'm going to say, is u less than or equal to the actual f of x divided by the upper bound of x? And if so, I'm going to, so if this, then accept. Otherwise, if this, accept. And add x to my set of points s. So suppose that I denoted, suppose this was x0, x1, x2, x3, and the set s was this set of points. If I end up accepting a point that's in this region here, that I had to get to the second step to determine that I could accept it, then I'm going to add this x to this set of points s. So part of the question is sort of why is it that I'm doing this? Well, the idea is that if there's a fairly large gap here, and if there's a big gap between f and the lower bound, the idea is the case that I'm gonna stochastically that's gonna sort of be obvious when I get a point falling such that the point is in between here rather than down here. And that sort of gives me an indication that that's a place where I can refine my upper and lower bounds to get a better sort of squeezing of f between the upper and lower bounds. So that's why I'm adding this new point to the set. And the idea is once I add this new point to the set, well then I'm going to draw in a new tangent line here. That new tangent line here is going to reduce the upper bound and get it closer to f. And it's also, as a result of drawing in the new lower bounds, it's going to get the lower bound closer to f as well. So the basic story is, as I proceed through this algorithm, I've got my f that I'm interested in, and eventually I'm going to end up with an upper bound that's sort of these piecewise lines that are very close to to f, and a lower bound that's also very close to f. So I'm almost always going to be in this situation here that I almost always accept, and I almost always only have to evaluate the lower bound and not even have to calculate f of x. So that's the basic story. Let's quit there. I can take questions about that on Friday. We'll finish off with important sampling on Friday and then move on to optimization.
Two questions.
Okay.
So, usually when we do it, numerically, shouldn't we have a cutoff on the tails of it? Because in the end, how you want for density is the add up to 1 and area of 1. And it's the maximum of the height. And some cutoff is already beyond the precision of the calculation, and whenever you add the area, no part is literally going to drop.
Sorry, I'm not quite following
So
you.
for instance, if you want to really distribution, you want to add the area of 1.
Yeah.
And in the end, what you do is really add up the numbers. So it's
You're basically doing a numerical integral?
yeah.
Okay.
So the maximum is like this, and whenever the tail is already very close to 0, then in the sum it's going to jump. So isn't that true that essentially it's always taking part of and not over range from negative instead of finite?
Well, you don't really want to do it that way because the values in the tail can be very influential, for example, the expected value of the variance and whatnot. So if, for example, I took a t-distribution, which has very heavy tails relative to a normal, and I arbitrarily sort of cut it off in this fashion, I'm throwing out all of these values, and if I then go to estimate the variance of this distribution from sampling from just from here to here, I'm going to underestimate the variance, because even though these have low probability, they're very large values, and so they have a heavy influence on, for example, the variance.
Then the problem for this kind of approximation becomes, it's not really limited in the finite range, and hence you have to keep going on to infinity. Even for just drawing the tangent lines, you have to really have a good approximation. Again, because it's not really bounded.
Yeah, then let's see if we can get it back to the original scale to see if that helps to see what's going on.
So for instance, the normal is going to be the example which goes indefinitely.
Okay. Why are you trying to?
Sorry.
I mean, so what does the normal distribution look like? The normal distribution looks like this. Okay. These are decaying as
exponential negative
squared, right? So what happens when we've got, so what does this upper bound look like? So we've got this tangent here. So we've got this, and now we're drawing a tangent here.
Yeah.
This is decaying off faster than this is obviously, but this is a straight line in the original space.
Yeah.
Now we exponentiate it. So it's basically decaying exponentially. So this is going to be decaying as e to the minus x. The upper bound is sort of decaying as e to the minus x, and the actual thing is decaying as e to the minus x squared, for example. So even there's more mass out here in this one, but we're still not going to sample out here very
I
often.
see. So at a certain stage, you just don't sample for the.
Well, you still do the sampling. I mean, basically what happens, and you'll see this.
Oh no, by
actually
sample I mean by drawing new tangent line or new approximation curve above the.
I mean, you do. So let's suppose that our upper bound looked like this.
Mm-hmm.
Here's one piecewise exponential. Here's another piecewise exponential. The basic strategy is you need, in order to sample from this, you basically figure out how much of the mass is in this piece, how much is in this piece, how much is in this piece. The amount of mass that's in this piece is going to be relatively small once you get far out into the tail, so you're unlikely to draw from there. But if you do draw from there, you're drawing from all the way out to infinity. So you can draw an arbitrarily large value.
Mm-hmm. And another question is, it's really better than interpolation of the, if you just want to sketch a function, which is hard, then one of the easiest ways is just have several points already.
Right, and that's how we can
Right,
do it.
and then just interpolate between the two. And is this going to be better than this method?
Oh, so you're saying that
So-
another way that you could sample from this is basically just come up with a piecewise
Yeah.
like this?
Yeah. That's the simplest numeric approximation of a function, right?
Yeah, I mean,
Depends
I
on
guess.
the curvature, usually, as far as the sampling is not too coarse, it can be a good approximation. And
Yeah, I mean, I
It's
guess
a little bit
I would say this is basically a more sophisticated way of doing that,
oh yeah.
right? So it makes sure that it makes sure that you get the exact right.
Because we do
density
have the
in each
function
interval.
form, right? We do have the function form. So in the end, the problem is it's hard to evaluate the density function.
It depends on what the function is. Yeah.
But anyways, the problem is it's hard, or it's computationally expensive to get the exact value of it. Otherwise, we just evaluate it. like the normal fiber functions.
Well, but just evaluating it doesn't give us a draw from the density. I mean,
Yeah.
the whole strategy here is to try and get draws from the distribution.
I see.
So you could have f of x being relatively easy to evaluate, but I still might not have a recipe for actually drawing random numbers from it. And then the first thing you might think of is maybe something like this. This is a more sophisticated way of sort of doing something like what you were.
So essentially,
doing
the
here.
problem is almost like if it's assuming that it's finite range for the point here, then it's almost like I'm randomly taking uniform values and just see whether that's within the curve or outside, and then accept it or not. And
Well, that is rejection sampling.
yeah,
That-
and that's
that-
just a much more coarse or less sophisticated way than
Right. I mean, this allows us to avoid taking all the samples out here.
wasted part
Yeah.
of it.
Yes. And it allows us to avoid having to. I mean, the other thing is you've assumed that it's finite, and I'll just draw a box above it, which is fine if that works, but you're going to waste a lot of effort here. And if it's not finite, then we need to deal with the tails, like I was saying. We need to find an enveloping function that we can have be above the tails always. So it gets more.
And the reason we don't really use the cumulative function and then do the inverse is because it's hard to do the cumulative, just like for the normal.
Yeah, it's either you can't compute the CDF or you can't invert it.
I see. Even numerically.
Well, right, that would be another strategy, which would be to try and invert it numerically.
So a good assumption when we want to use this is either the cumulative CDF is hard to calculate and the inverse is expensive, or for some reason we don't go for that more standard approach.
Right. I mean, right. It's if doing the CDF is either you can't do it analytically or doing it in a numerical fashion would be difficult. I mean, once you get to having to do it in a numerical fashion, you're basically having to do a bunch of calculations. You have to do a bunch of calculations.
So
here.
it's probably not worth it than doing. So it's probably not worth it to do the CDF than doing.
I mean, if you can do this, this is a good algorithm and it's well established. So
I see.
rather than messing with the numerical, trying to do numerically invert the function, you might as well do
I see.
something like this. If the property is satisfied such that this will work, the concavity gets.
I see. All right, thanks. Oh, by the way, I'm not assigned because I'm only auditing this class.